So, welcome everyone to our weekly seminars. Today's speaker is Quentin Vigneron. Quentin did his PhD at the ENS de Lyon, and then he got his first postdoc at the Copernicus University in Toruń. Then he won a Sonatina grant, and now he's affiliated with both Poland and France. He has been working on a modified theory of general relativity. This modification comes with a topological factor. And today he's going to talk about some physical implications of it, right?
Yeah, in particular. Yeah.
Okay, floor is yours.
Thank you for the introduction. So, as you said, I will talk about the modification that I have proposed recently, which you can see here. I will not only talk about the implication, but also why it's interesting to motivate. It's interesting to consider this modification. And so the outline of this presentation is as follows. I will first present this theory. We'll say that it's quite simple to understand what is the physical differences between that modification and general relativity. We'll see what are the motivations for considering that modification, and I will focus, there are several of them. I will focus on one, which is related to the Newtonian limit, which was the initial topic I was working on during my PhD. And that some of the results I obtained by working in this field led me to modify the Einstein equation. Then there are several consequences, applications that we can do with this equation. I will not talk about every one of them, like there's black hole, there's a variation principle, etc. I will focus on the application which is closest to observations and which actually can be tested. And this is with respect to cosmology. So I will present a test of this theory, and then I will talk about, at the end, about how inflation can be dealt with in theory, how it's better dealt with than in general relativity. The whole context of this talk is what we call the topology of the universe, or cosmic topology. And so I want first to introduce the basics about this notion. So cosmic topology is the study of the shape, or precise topology, and global curvature of our universe. To understand a bit more what is meant here, we can take the simple example of the standard model of cosmology, in which we have three possibilities for our universe, either Euclidean, spherical, or hyperbolic, and that are characterized by what we call the spatial curvature, and more precisely the sign of this curvature, this parameter k here. In this standard model, this curvature parameter, omega k, enters into the equation for the expansion law, and as function of the sign of the curvature, we have different expansion scenarios. So I forgot to put the graphic here, but basically we have this really known graphic that as function of the sign of curvature, we can have a rebound, an acceleration, or just an infinite expansion like this. Okay. So this is a well-known thing, but usually it's said that these are only three possibilities, but in reality, they correspond to a family of possibility, in a sense that if our curvature is, for instance, flat, zero, it doesn't mean that the universe is necessarily infinite. There are a lot of possibilities, and what they correspond to is that they correspond to choosing a shape in this Euclidean space and making the space periodic with respect to that shape. So for numerical people here, this corresponds as choosing periodic boundary conditions. In the numerical aspects, it's for technical reason that we do this, but in reality, for our universe, this is totally possible. This is what we call a topology for the universe, which in the case we consider a cube as periodic boundary condition in a flat space. This is called a torus topology. All of this to say that in each of these three possibilities that are in our standard model, we have a family of possible shapes that periodically tiles those spaces here. So here it's just a two-dimensional drawing. What we would see in 3 dimensions is due to this periodicity, we could observe identical images of the same object in different direction in the sky. Here, this is the example of our planet. In reality, we would observe identical galaxies in different direction, position, and distances, or different clusters of galaxies. Okay, and this is the mathematical structure that is behind this thing. Now, the fact that our universe can have this periodicity is not an exotic consideration. It's actually implicitly present in our standard model of cosmology, because we always need some kind of boundary condition to solve the equations and to predict the physics. And the only physical boundary condition we can consider is to consider those kind of periodic spaces. Okay. So we have two notions: the notion of the global curvature that determines the family in which our universe is, and the notion of the shape that determines the precise periodicity of our universe. I will mostly be interested in which family are we living in, and I will not be that much interested into what is the precise shape of our universe. But still, I wanted to present this to show exhaustively what were all the possibilities. Now, this is in theory. We can wonder what about observations? And both of these aspects, shape of our universe and global curvature, can be tested with current data. If we consider the shape, what we are looking for is those identical images, either in catalogs of galaxies, and we have like specific spikes in the correlation, or directly in the biggest map that we can observe, which is the CMB Cosmic Microwave Background Map, where we search for identical circles in this map that would indicate this possible periodicity. And as for now, we didn't detect anything, and we only managed to obtain a constraint on what is the minimum size of this periodicity, which is basically just a bit less than the size of the CMB. So it's still possible that our universe is not infinite, but it's if it's not infinite, then its size is at least around the size of the CMB or bigger. Now, in terms of the curvature parameter, which is what I will be mostly interested in, then again, using the CMB map and coupled eventually with catalogs of galaxies, then we can have a good constraint on this parameter omega k to be, and the current best constraint is that it's 0 plus or minus 10 to the minus 3. So it's very big. This means that the curvature radius of our universe is at least like 10 gigaparsecs, something like this. Okay. There are, however, some debate on whether on some different analysis of the CMB data that led to a negative curvature parameter. And this is sometimes called the curvature tension. It's not yet sure that there is real tension, but just to say that there is actually a debate whether or not we really have this huge constraint, or if actually we already measure a non-zero curvature. All of this to say that there is a growing interest into the study of cosmological model, including global non-zero spatial curvature. So either in the data analysis and in the theory for either structure formation and for inflation, as we will see at the end of the talk. This is basically all we need to know about the context of cosmic topology, and especially about curvature. Okay. I will come back to this measure at the very end when I will test my proposed theory with observations. So now let's enter the main topic, which is that equation. Okay. So this is I would say, the most technical part. So I will not go into more details into the mathematics behind those equations. What is that theory? So that theory has two components. It has the same component as in general relativity. That is to say, a metric, a Lorentzian metric with a connection. The metric gives a way of defines how we measure distances, and the connection defines how we compare objects in two different positions in space-time. And in this theory, there is an additional connection, this nabla bar, that comes with a curvature that I call the reference curvature. which is not present in general relativity. And the Einstein equation is modified to feature this reference curvature. So GR is that equation without the red term, and here we replace our mu nu, which is a space-time curvature, by the difference between the space-time curvature and this reference curvature, which is non-dynamical. So it's a simple modification, and the fundamental thing is that that term here is non-dynamical, so it doesn't add any degrees of freedom compared to GR, doesn't add any additional parameters. And the fundamental feature is that it's fully fixed by the topology of our universe. How is this done? If we come back to these three possible topologies that are included in the standard model, then as function of which one we consider, this reference curvature has this one of these three forms. So we see in particular that if our universe is globally Euclidean, that term is zero, and therefore the equation is equivalent to GR. So this theory is equivalent to general relativity in the case our universe is globally Euclidean and differs from general relativity for any other possible topology for our universe. It's unique for a family of topologies. So if I choose a topology in the spherical family of topologies, then it's fully fixed. Same here. And in reality, I didn't present it, but there are actually other possibilities, 5 other possibilities that are not included in the standard model because they require additional parameters, and so it's a bit less simple. But this modification is really general for all the possible topologies we can consider for our universe in 3 dimensions. And in general, this term has this form. Okay. So now it might still seem a bit abstract to you. Just we add this term, which has this form with those topologies. It would be interesting to understand what physically is the difference when we consider that equation instead of GR. And so for this, we can come back to the usual interpretation of what is the Einstein equation. So this is the Einstein equation. On the left, we have the space-time curvature, the curvature that is related to the metric. On the right, the matter content. And we have this usual interpretation that, okay, the role of matter is to curve space-time like this, because in absence of matter, so energy momentum tensor being 0, space-time is flat. In vacuum, it's flat. Here it's totally different. In vacuum, right-hand side being 0, the space-time curvature, this R mu nu in black, is not necessarily 0. It equals to this reference curvature. And so what we have is rather this picture where in vacuum, space-time is not flat. It's curved by the topology of our universe. And so the role of matter is not anymore to just curve space-time, but the role is to deviate, induce a deviation from the curvature that is imposed by topology. So we rather have this picture where this donut represents the topology and the curvature that is imposed by topology. And we have those deviations that are induced by the matter when it's not in vacuum. Okay. So it's qualitatively how we can understand this theory. And once again, it's really simple in the sense that this parameter is fully fixed. So compared to other modified gravity theory, it's basically way more simple in the sense that there are no additional degrees of freedom introduced. And in particular, you still have the equivalence principle, conservation of energy momentum tensor. It's still an equation which is a second order equation in the derivative of the metric. And so we are really close to be as simple as general relativity. Okay. But now the question is, why do we want to consider this? Why do we want to modify the Einstein equation as function of the topology of our universe? So, as I said, I forgot to put it here, there are several independent motivations that I found. I will focus on this one, which is the one which made me consider first this modification, and which is related to the non-relativistic or Newtonian limit. So for this, we will consider this scheme, okay? Where in this column I consider a universe with a Euclidean, globally Euclidean topology, and here any other possibilities. Okay. Now in this first line, I consider the relativistic regime of gravitation, which in the current paradigm is described by the Einstein equation, and which is described by the Einstein equation regardless of what topology we consider. We can consider the Einstein equation for a spherical universe, hyperbolic, or Euclidean. Now, if we consider the non-relativistic regime of gravitation that we would obtain by a limit where we take the speed of light to be infinite, that regime is described by Newtonian equations, cosmological Newtonian equations that I recall here, I mean, some of them. But because in that theory, spatial curvature, which is here, is exactly 0, those equations can only be defined on a universe which globally is Euclidean. So what this means that we don't have yet a theory that would describe non-relativistic gravity or Newtonian gravity, if you prefer, on a universe which would be spherical or hyperbolic, for instance. And so the first two questions I was interested in during my my PhD was how could we, what would be the equation that would describe a Newtonian gravitation in a spherical universe, for instance. And once we obtain those equations, are they compatible with general relativity, as it is the case for classical Newtonian equation in the Euclidean case? There are a lot of ways of obtaining Poisson equation by performing a limit of GR. Okay. So these were the questions I was interested in. Okay. And the answer to that question is what led me to modify the Einstein equation. So here I will sketch what are the main ideas behind answering those questions, and why at the end the answer to this one will lead to a modification here. So the first thing we want to understand is how do we obtain Newtonian gravitation in a universe which is not globally Euclidean. So for this, the thing is that we cannot say, okay, Newtonian gravitation is something defined on a flat space, because if we do this, if we start from this, then we are locked on this thing. Rather, it's better to start from what is the fundamental principle of what we call Newtonian gravitation, and it's the fact that it's a theory which is invariant under Galilean transformation. And if we start from this point, then there is a nice, very beautiful mathematical object that we can use, which is called the Galilean structure, and which is somehow the equivalent of this, the metric we have in general relativity. In general relativity, this is a theory which is invariant under Lorentzian transformation. So we have a light cone that defines causality. And if we start, if we say we want Lorentzian invariance, then this tells us that, okay, we have to use this metric, which has a specific signature. Okay. Now, if instead of this, if we say, I want causality to be defined by Galilean invariance, so we rather have this picture with a fundamental space and a fundamental time, then we can show that there is a this object, this metric, is replaced by this kind of object here, which I will not detail in precision. All of this to say is that by using this object, which is basically the most fundamental mathematical object we can define from Galilean invariance, we can show that there is basically a unique way of writing equations that are Galilean invariant and that are defined on those topologies. And what is kind of remarkable is that this unique way is basically just the same equation, but the only difference is that in this Laplacian there is curvature. The spatial metric which is present in the Laplacian of the Poisson equation, there is curvature. So it's really beautiful, because if we would have wanted to heuristically guess what would have been the equations there, it's basically what we would have guessed. But it's beautiful because if we start from just Galilean invariance, we can show that we don't have more other possibilities. It's the only thing that we can consider. And okay, so this fills this hole that we had in this scheme. Basically, this whole line corresponds to Newtonian gravitation in any possible topology for our universe. Now the question is it compatible with general relativity, as these equations are in the Euclidean case? And for this, we have to wonder, okay, basically we have to take the Einstein equation, perform a Newtonian limit, and see if we can obtain this equation. Once again, this is something that we can do by using fundamentally symmetries. And we can define Newtonian limit in any of those possibilities for our universe. And the remarkable result is that the moment we say we apply the Newtonian limit on the Einstein equation, then we cannot do it if our universe is spherical, hyperbolic, or any other thing. In other words, this means that if we start from the Einstein equation and we say we take the Newtonian limit, we can only do it if additionally we assume our universe to be globally Euclidean. A consequence of this strong result is that if our universe is spherical, then if we use the Einstein equation to make some prediction or to measure things in the universe or predict, for instance, a rebound like this, and in the same time, if we use Newtonian gravitation at any scale, even the solar system scale, this result says that it's mathematically incompatible. And saying that, we can be a bit, it can be a bit uncomfortable because Newtonian gravitation, like Galilean invariance, has proven to be really precise at a lot of scales, and it's not nice to use like two theories for describing two different regimes of gravitation, which are not compatible. It's like if we would use a quantum field theory, which doesn't have a classical limit. And so from this, we could say, okay, maybe we would like compatibility, and maybe we would like a relativistic equation that admits a Newtonian limit regardless of the topology of a universe. And so in other words, we ask the question, what is the modification that allows to have this limit regardless of the topology? And the answer, or at least the simplest answer I found to that question, is this theory that I presented just before. So to recap here, the argument is to say that if we require relativistic theory of gravitation to have a Newtonian limit regardless of what is the global structure of our universe, then we shouldn't consider the Einstein equation, but we should consider that modified equation. Okay. So this was the result that led me to this modification. Now let's see what are the consequences for cosmology. Why cosmology? Because since we modify the Einstein equation, there are differences at all scales, like for black holes, for emission of gravitational waves, etc. But because that term depends on the global structure of our universe, and because our universe a priori is actually big, we expect observational consequences to be present only at large scale. And so to try to confront this modification with observation, it's better to look at the consequences for cosmology rather than for black holes. Okay. So the first thing we can do is just calculate the homogeneous anisotropic solution of this modification. And already here we have a really interesting difference. So on the left we have general relativity, for the record, where I recall that there is the presence of the special curvature that leads to different scenarios as function of the sign of the curvature. In this case, the expansion laws are the same regardless of what is the value of the special curvature. What this means, it means that in this theory, the expansion law is always this one for all curvature. The expansion is always the same regardless of what is the curvature of our universe. Another way of framing it is that in this theory, the curvature doesn't have any more, special curvature doesn't have any more effect on the dynamics of the universe. But it's still present geometrically in the sense that we have this special curvature, so it distorts how light travels in the universe. And so this means that if we want to, it's still present in the distance, angular diameter distance relation, for instance, which is a fundamental relation we use in cosmology to measure the parameters of the standard model with observations of galaxies or CMB, etc. In this formula, in general relativity, the curvature appears in two different ways. In this function, which comes from the metric, from the distortion, the lensing due to the curvature. So it's a geometrical effect, which is present in both theories. And in general relativity, curvature also appears here where we have h, the expansion rate, because curvature appears in the expansion law. In this theory, in that formula, curvature doesn't appear anymore here. I forgot to say that sometimes I named it theory topology for the topological modification. And so we see this, and so the whole question, if you remember, I said that the current measure of curvature is basically that it's 0 plus some uncertainty. So the question is, okay, is this measure actually a measure of the dynamical effect curvature has, which is not present in topology? So is it a measure of something which is in this theory 0 by default? Or is it a measure of curvature through its geometrical effect, which is present in both theories? So the question basically is, okay, if we reassess the evaluation of omega k from observation, do we still find something basically 0 with that modification? Or is there like a non-zero curvature that appears? For this, let's try to understand how curvature is measured. It's with the best measurement we can get, which is from the CMB map. So on the left, we have the CMB map, and on the right here, the power spectrum of the fluctuations here. And so there are two, in general relativity, as I said, there are two effects, dynamical and geometrical. The geometrical effect, it tends to change the way the size of the structure that we see. For instance, if our universe is positively curved, then we will tend to see bigger structure. There will tend to be a kind of a global lensing that would lead to structure that appears bigger than they would be in a flat space. What this translates into this spectrum, where in the x-axis we have the angular scale. So here on the left is this corresponds to the biggest scale. This translates into this modification. If the curvature is positive, basically the whole spectrum is shifted on the left. If the curvature is negative, it's shifted on the right, on the smallest scale. And so by measuring precisely where those spikes are, then we can measure the, let's say, geometrical special curvature. Now in GR, it also has a dynamical effect. It's a bit more subtle to understand how it affects the spectrum, but basically, and there is not yet a full consensus on how it is affected, but basically what we can say is that it affects the amplitude on these scales here, which are the scales that are measured with the less precision in the CMB. And there are also some factors that comes from the initial condition on how curvature affects this. But so here we see that basically the dynamical effect is measured here where we don't have much precision, and the geometrical effect is measured where we have a really huge precision on where those peaks are. And so the consequence is that our current measure of curvature, basically 0, comes from the geometrical distortion of curvature, which is also present in my model. And so the consequence is that if we fit the data with this model, we don't see much difference with the standard model. So if you look at the first graphic here on the left, where I use Planck data plus some galaxy catalogs. So in blue, this is the standard model, and in red, this new model. We see that there is not much difference. The two fits are the same. So these graphics represent like one parameter as function of the other one. So for instance, if we look at this square here, we have the curvature parameter as function of the Hubble constant. And basically, it's still around 0, plus or minus, not much. Okay. Now, it's a bit richer, what we can say, if we just take a single set of data and we do the analysis, as it's done on the right-hand side here. And in particular, if we consider only baryonic acoustic oscillation plus supernovas, we see an interesting difference, which is that, okay, so here it's in blue, my model, and in red, the standard model. We see that we have still a curvature, which is measured to be around 0, okay? But the direction of degeneracy between the curvature and the Hubble constant are orthogonal. And so while we cannot here distinguish between the two models, this suggests that if the true curvature of our universe is not 0, with better precision, due to this difference in the degeneracy between the parameters, we might in the future be able to distinguish general relativity and this model. But as for now, the conclusion is that we cannot do much. The two models are equivalently good at fitting the data. But it's not, so we have to wait. But in the meantime, what we can do is come back to theory. So it's a theory that led me to consider that modification. And so as for now, it's the biggest motivation. Maybe in the future, some observation will motivate this. So now if we come back to theory, but still staying in cosmology, we can have a look at inflation, and we'll see that there is a really beautiful result that appears that if we do inflation in the context of this theory, while having some special curvature, then inflation is basically well-posed and behaves better than if we would do it in general relativity. So to understand this, let's talk about just the basics on inflation. So if we consider just a standard Big Bang hypothesis without inflation, we have this evolution of the scale factor of the universe, the size of the universe as a function of time, with a divergence at finite time where the scale factor tends to 0. Okay. One of the problems of this, on top of having this singularity, is that if we consider this evolution of the scale factor and we look at the CMB map, on the CMB map, on two opposite sides of the CMB, we see the same physics, the same statistics, the same temperature, the same power spectrum. So what this means that the two opposite sides of the CMB, this suggests that they were in causal contact at some moment in the life of the universe. But we can show that if we had this evolution of the expansion of the universe, we can, with a kind of finite time here, we can show that this prevents at the scale of the CMB any causal contact. In other words, this we see basically a homogeneous CMB where the physics is the same everywhere, but this is not possible if we have something like this. And the idea of inflation is to say that, okay, maybe we don't have a sharp drop to 0 here. Maybe we have a phase of acceleration that starts at some point. We don't know what was before, but that a certain phase of acceleration that lasts for some time. And if we assume this phase of acceleration or inflation, then we can show that this provides an origin for why the universe looks the same in the universe. The CMB looks the same in any direction. So it provides an origin for the causality of the cosmic microwave background. And this phase of inflation is most easily realized by assuming that early in the universe, where matter was really dense, we don't know the precise physics that was behind this state, but we can assume that effectively the matter was described, or the matter size, energy momentum tensor, was described by just a single scalar field. We don't say that this is a fundamental scalar field. We say that, okay, it's an effective description of what was the state of the matter there. If we do this, we assume scalar field in the energy momentum tensor. Then we have naturally a phase of acceleration, which provides this thing. So assuming this simple hypothesis, we solve this problem of causality. This is at the level of homogeneity, but something which is really strong and that made the success of inflation is that if we look at the level of the perturbation, where we see this power spectrum, with this simple assumption, we can also give an origin for this fluctuation, this power spectrum that I showed for the cosmic microwave background. How it is done? For this, we need to consider the what we call the weak field equation, which are the perturbation around the homogeneous solution of general relativity. In those, there is a full set of equations. One of these equations looks like actually the Poisson equation, like this one. And then we do, okay, we put in the matter side, this density, we put this scalar field. And what we obtain is that at first order, we have only one equation left, which is that equation, which is a wave equation, like a Klein-Gordon equation, with some kind of damping term. Okay. So it's a really simple equation, and it's beautiful because it's something that we know how to quantify canonically. And since we are at the state of matter which was really dense, we can assume that at that stage, matter was in a quantum state. And so what we can do is that, okay, we say that initially, in the initial phase of the acceleration for the inflation, we had this quantum state. We have this nice equation for the perturbation of the scalar field. We take a quantification. And what is really beautiful is that if we say, okay, what is the initial condition? We assume the simplest hypothesis, which is to say it was the lowest energy state, which we also call the vacuum state. And we say, okay, acceleration began basically in the vacuum state of the scalar field. What we can show is that this means that initially the power spectrum had to be basically flat, a white noise. And if we evolve this flat power spectrum after the acceleration with the known physics, thermodynamics, biogenesis, baryon, dark matter, etc., the evolution of this power spectrum exactly leads to what we observe precisely on the CMB. And so this is really what made the success of inflation, because basically you take all the simplest hypotheses, the simplest thing you can put in the energy momentum tensor, scalar field, the simplest initial condition after quantization, and you explain both this and this, where basically it's not just you explain one point, you explain thousands of measurements which corresponds to each of those points. And so it's really important here to understand that one of the main reasons inflation is in the paradigm is the fact that it's very simple and natural model that gives an origin for the initial condition at some time of our universe. Why do I talk about this? It's because maybe you saw it here. All of this is in the case, I assume, globally Euclidean universe. What happens if, okay, I consider the universe to be spherical, for instance, so k different from 0. Let's start again. First thing that happens is that due to this curvature that is present in the expansion law, then we don't anymore have this acceleration with a scale factor that tends to 0. But in particular, in the case where curvature is positive, we have a rebound. So it's a opposite rebound that the one we had here. Okay, and this leads already to a little problem because of this rebound, if we want to provide an origin for the causality of the CMB, so the homogeneity, we need to add some assumption on what is the value of the special curvature. We have a lower maximum bound on it, such that we manage to explain this. And so we already need to add some tweaking to the scenario. But it's still not yet full pathological. We can still provide this and it can still work. But now, okay, perfect. But now what happens for the biggest part, which was like the fact that we predicted in the flat case, the full power spectrum of the CMB. So for this, we can again do the same procedure. We look at the weak field equation. which, because there is curvature, they are a bit changed. And in particular, for the example I took, the Poisson equation, there is this additional curvature which is present with the Laplacian. And the consequence of this difference in the weak field equation is that now we don't have anymore this nice Klein-Gordon equation I presented, but we have this ugly fourth order differential equation here. And this is a huge problem because this is something that we don't know how to quantify. And it's not even that we don't know and maybe there is a way. It's like, it's not possible. The way we can show it's not possible is that if we try to derive this from a Lagrangian, then we need to inverse in the Lagrangian some Laplacian, some non-local operators. And so there are a lot of technical things that prevents us to do any quantification of this. And so this means that there is not anymore a natural way of choosing the initial condition as the lowest energy state of this scalar field. Basically, energy state is not anymore defined in this context. And so this whole nice, beautiful procedure is not anymore possible. And so what this means is that if our universe is spherical or hyperbolic, regardless of the value of the spatial curvature, then it's way more complicated to do inflation here. There are a lot of papers trying to do it, but all of them, basically, they introduce eventually fine-tuning, a different mechanism, an additional phase of pre-acceleration. They say, okay, we assume that initially the curvature was already fully negligible. But they add a lot of hypotheses, which impairs a lot on the simplicity and the naturality that made the success of inflation. And so we can really start to wonder that if we will want to accept this, in the sense that inflation is still a hypothesis, we don't have a fundamental theory showing that it existed. So the main argument is the simplicity, and here we lose a lot of the simplicity. So this might be considered as really a problem. What happens in my modification? Let's come back to this modification. So here I consider it for any curvature. So I recall that for flat curvature, it's equivalent to general relativity. Okay. Because for the same reason that for the evolution in the future of the expansion is the same for all curvature because the curvature is not anymore in the expansion law. This works also in the past. Regardless of the value of the curvature, we always have this, what we had in the flat case in GR. And so this means that this first problem that we had, that we needed to tweak a bit the value of the curvature to solve the causality of the CMB, is not anymore present. We always provide an origin for the causality, for the homogeneity of the CMB, regardless of the spatial curvature. So already at that stage, it behaves a bit better. Okay. What about now the perturbation and the power spectrum? So this, don't need to understand this equation, but basically it's just to show what are the differences. On the left-hand side, these are all these perturbations equations that I presented in general relativity, where in blue, these are the terms involving the curvature that appeared, and which were responsible for this ugly equation, which was not anymore a wave equation. Now we have obviously a bit different equation for this modification, where in red we have those terms that depends on the curvature, and so we have different sort of equation. And what is kind of a miracle and really beautiful is that the difference between the two, and how the curvature appears, it's precisely the difference that leads to having this nice wave equation for any curvature. So, in other words, we have a modification as a function of the curvature, and that modification is a posteriori, it's not made for, it's just a result that I obtained. Is precisely the one that leads to that nice wave equation we had in the flat case, but here regardless of the curvature. And so, because we are like in the flat case in general relativity, we can do the same thing. We do a canonical quantization of the Klein-Gordon equation. we take the rawest energy state, we found a flat power spectrum, which is what we had here. And so in other words, in this theory, inflation is simple and natural regardless of what is globally our universe. And so here it's really an Occam's razor argument, that if we want a universal, because we don't know yet, inflation is always a motivation for indent respect.
Something happened to sound. There's no sound.
What? To the topology that is
Is it
or the Ricci tensor.
you know what I mean? They also have to use also should be.
There's still no sound.
Yeah. term, but there is no part side, but the matter side.
No, there's no sound.
So thank you very much for principle from which you can derive
Time. We can. Preferred for velocity. Constrained by the tilt between that.
Just-
the curvature. Or south. To zero, and then I
Was any motivation? So
reheating will naturally occur. These are usually calibrated using maybe we can talk about that later.
So it was in collaboration with that guy
Yeah,
who is
Vigneron.
more specialist on the
Yeah.
Vigneron Poulain. From my understanding, no, this is what I showed you. So the CMB is replaced by supernova data, and what I mean by supernova is like Pantheon plus, so you don't use Cepheid, I think. And I think with the combination allows you to have two measurements of the sun horizon, and it's okay. I think this is. I'm not fully sure, but I think it's yeah. There is really no CMB there, and because BAO alone, you cannot have this measurement. You have a degree of degeneracy, but which is.
So I think my point is that BAO plus supernovae without Planck may already have Planck in it because those surveys from BAO use it to calibrate the baryon to photon asymmetry from
then
Planck.
I don't know. Yeah, I see.
And that is technical. I mean, yeah, that was it.
Yeah,
We
I
can
don't know
look at that later.
Okay.
Thank you.
Do we have questions from Zoom? No? Maybe they right? Sorry? Okay, you have questions. Sorry.
I mean, in the beginning, you said like topological method actually doesn't boil down to the Poisson equation in the non-relativistic limit.
Yeah.
And that means in locally you can detect this curvature effect in anywhere. I mean,
Yeah, in theory, yeah, but since in practice the curvature is really small, I mean it's like or almost zero, then it's not possible. I mean, it's an interesting question because, for instance, in just classical Newton with Poisson equation, already if you assume infinite space, you have like gravitational potential, which is 1 over r. If you assume, like in numerical simulation, a torus, periodic condition, then the gravitational potential is a bit changed. There are additional terms due to 1 over r plus things, which it's called the evolved summation. But there is a difference in how the gravitational potential, the function of the gravitational potential, because of topological things. It's the same here. If you have curvature, then the gravitational potential will be 1 over r plus a correction that comes from the curvature, for instance. But this additional term is proportional to the size of the system you study over the curvature radius of the universe, which is at least 10 gigaparsec. And so if we consider the solar system, then it's impossible to measure the correction. So the answer is yes. In principle, there are correction terms due to the presence of this curvature in the Laplacian, but absolutely impossible to measure locally.
So in your method, you can reduce this complicated equation to simpler equation using this topological background, right? I'm talking about another question.
Yes.
But that means you can solve this complicated differential equation using your method.
Which complicated equation are you
Like,
talking
for
about?
example, you compare both, like when you consider the curvature.
Yes.
If you without using your method, the equation is very complicated.
For inflation,
Yeah.
for instance?
Yes.
Yeah,
In
yeah,
that
yes.
case, you can even solve this complicated equation using this background method.
Yeah, so I go from, so you're talking about this complicated equation. Yeah, so yeah, you add this background term, this r bar, and then this equation becomes this equation. Yeah. So it's really, it's really mostly yeah, simplicity arguments. Like we have this like a way simpler theory that leads to a way simpler equation, and then it's like not philosophical, but it's like usually in physics when we have a theory which is not yet tested, inflation is not yet tested, we usually want to take the simplest thing, and this is the simplest thing we can take.
Okay, let's wrap it up. We're going to continue our discussions at the coffee room. Anyone can join. Thank you.